Hello everyone, my name is Malaika Chaudhary and today I'm going to explain the mechanism of the alpha halogenation of aldehydes. As the name indicates, it is the halogenation of aldehydes at the alpha position. Halogenation means the addition of halogens, the substitution of halogens and aldehydes. Right here is the aldehyde. This aldehyde can be written like this because we know on the left side on the left side of the carbonyl there is a methyl group. There is a carbon and the three hydrogen are attached to this. Here is a different presentation of the aldehydes. Next to the carbonyl, there is a carbon and it has three hydrogens. This carbon is known as alpha carbon because of its position. This position is the alpha position and the carbon is at the alpha position, which means it's the alpha carbon. All the hydrogens that are attached to this carbon are known as alpha hydrogens since they are attached to alpha carbons. These hydrogens are tend to be very acidic. So whenever a base reacts with them, the base will extract the proton immediately. Here's the enol structure of the aldehyde. Whenever aldehyde will make the halogenation, first the enol structure will form, and then the substitution of the halogen will occur. Enol will form in two different ways. The first is acidic conditions, I mean using acid, and the second is base. So we can form enol with the base catalyst or with the acid catalyst. So now we will talk about both ways. Here is the enol formation in acidic conditions. First of all, we have our aldehyde right here. One lone pair means two electrons will move to the hydrogen, and then hydrogen will move those two electrons to the base attached to it. This will make a hydrogen-oxygen bond, as we can see right here. But as oxygen moved its two electron, like mean lost to its one lone pair, it will have a positive charge. The carbonyl oxygen is protonated, and it will give a cation by two resonance structures. As we can see, there are two resonance structures. Then one, the positive sign is on the oxygen, and in the one, the positive sign is on the carbon next to the oxygen. After that, the base that got the two electrons that got the lone pair from hydrogen or from oxygen will then react with the alpha hydrogen, and then it will give two electrons to the alpha hydrogen, and then that will give two electrons to the positive charge next to the carbon next to it. So like there's a movement of the four electrons. This will make our enol and Ha again, like our catalyst again. So we use this catalyst in the beginning to make enol, and at the end we remade it, so we didn't use this catalyst. Let's take a look at the enol formation in basic conditions. The one main difference in the enol formation in acidic and basic condition is that in acidic condition, the lone pair from carbonyl oxygen will react with the hydrogen and make OH bond, and then the base will react with the alpha hydrogen. But in basic formation, it's opposite of it. So first, the lone pair from the base, the catalyst that we're using, will react with the alpha hydrogen, and then the oxygen hydrogen bond will form. So it's like opposite. The basic and acidic condition are opposite of each other. So right here we have our aldehydes, and here we have our base. So the lone pair from base will transfer to the alpha hydrogen, and then alpha hydrogen will move those two electrons to the carbon next to it. So which means the base will remove acidic alpha hydrogen, and it will end up making an anolate ion, and that will have two resonance structures, as we can see right here. In the first one, we have negative charge here. The negative charge is because of the two electrons that came from the base, and in the second one, this negative charge moved to the oxygen next to it. After that, the protonation will occur, and the protonation of the enolate ion on oxygen gives the enol and regenerate our base catalyst. So now we have talked about the enol formation with the basic catalyst and acidic catalyst. Let's take a look at the mechanism by using acidic catalyst. Here's our aldehyde. We are using acidic catalyst. The acid catalyzed the enol formation will occur, as we have talked about this earlier, like how acid catalysts work and form enol. So the next step, we can see we have our enol. The two electrons, the one lone pair from the oxygen, will move to the carbon right there, that is right next to the oxygen, and then the two electrons that are present right here in the double bond will move to the electrophile, and it will end up making a CH3 bond, because this carbon has two hydrogen bonds. This carbon will make a one bond with the electrophile, will have hybridized sp3. An electron pair from the enol oxygen is moving to the electrophile and is making a new bond. It will leave the cation intermediate that is stabilized by two resonance structures. As we can see right here, there are two resonance forms. The positive sign is on oxygen, since oxygen has lost its two electrons. In the second one, the positive sign is moved to the carbon next to it because of the resonance. Then our base will come that has a negative charge, which means that it has electrons. It will react to, it will move two electrons here, and then there will be two electrons to the positive sign next to it because it is lacking electrons. So it will end up giving us our product. There is a loss of proton from oxygen, and it yield a neutral alpha substitution product as a double bond between carbon and oxygen right here. We have our alpha halogenation of aldehyde. As we can see, here's our electrophile. This electrophile is the halogen as we are doing the halogenation, and this is at the alpha position. So that's it for this reaction. Thank you.